I want to ask you something. What if we could build a perfect digital copy of our universe? I'm not just talking about simulating the weather. I'm talking about simulating the very fabric of reality itself. Well, today we're going to dig into a concept that tries to do just that. No, really, let that sink in for a second. We're not talking about simulating things in the universe, like weather patterns or galaxy collisions. We are talking about building a simulation of the universe from the ground up. This incredibly ambitious idea has a name, the Numeric Fabric. So, what is this thing exactly? Well, at its core, the Numeric Fabric doesn't start with all the complex equations of physics we know. Nope. Instead, it starts with something way simpler. It's just two things: a massive, massive grid of individual points and the rules that tell them how to connect to each other. To really get a handle on how this works, we're going to build one ourselves step by step. First things first, we've got to lay the foundation for this brand new digital reality. Okay, so forget everything you know about atoms or quarks or strings. We're starting with something even more basic in this digital universe: a single dimensionless point in space. This is our fundamental Lego brick. Everything, and I mean everything, is going to be built from this. So a single point all by itself is, well, kind of boring, right? The real magic starts to happen when we connect them, when we start weaving these individual points into a coherent fabric. It all starts right here, with just one single building block. But to create any kind of structure, this point needs neighbors. And the fundamental rule of our entire grid, the thing that makes it all work, is the exact number of connections each point has. And that number is 12. Every single point connects to exactly 12 of its neighbors. This specific number creates an incredibly stable and uniform structure. You know, the perfect, consistent foundation you'd want for a simulated reality. Now, this arrangement has a pretty technical name, but it's way easier to just think of it like this. Imagine that all the connections between these points are like tiny, tiny springs. When all of those springs are perfectly balanced, not stretched, not compressed, the entire grid is perfectly stable. It's like a motionless, perfect crystal. Okay, so we've built ourselves a static digital crystal. That's cool, but our reality isn't static, right? It's got motion, it's got waves, particles, energy. So how does this model get from a frozen, motionless grid to a dynamic universe? Well, the secret is in how it handles time. And that brings us to the next piece of the puzzle. We're about to dive into how this model actually calculates movement and simulates the flow of time itself. The system does this using a really clever method. It always keeps track of two previous moments in time. Think of it this way. To know where you're going, you need to know where you are now and where you just came from. The computer stores the entire grid's state at a far past moment, we'll call it T1, and a recent past moment, T2. It then uses the information from both of those to calculate the very next moment, the future, at T3. So how does it actually calculate that future position? Well, for any single point, its brand new location is figured out using three things. First, its most recent position. Second, its speed and direction, which it gets from its past movement. And third, and this is the really key part, the collective pull from those 12 spring-like neighbors. This massive calculation happens for every single point in the grid, at every single tick of the simulation's clock. All right, so we have a grid, and it can simulate motion. But so far, you might be thinking, okay, that's an interesting computer model, but what makes this a real breakthrough? And that is what this final section is all about. Because the real innovation here isn't the grid itself, it's the intelligence that's managing it. This right here is the real dividing line. The grid structure, that face-centered cubic thing, and the method of calculating the future from the past, those are established computational techniques. They've been around. The true revolution here, the game changer, is the layer of artificial intelligence that manages this whole shebang. The novelty isn't just the grid, it's how an AI uses the grid. See, the AI doesn't just manage this unbelievably complex system. Its main job is to hunt through the simulation, constantly searching for emergent patterns, for vibrations in structures that behave just like the fundamental particles of our own universe. And let's be crystal clear, this isn't about making a pretty light show. The AI is hunting for stable, repeating patterns of vibration. It's looking for structures that behave like the two fundamental types of particles in our universe: fermions, which are your particles of matter, like electrons, and bosons, which are your force-carrying particles, like photons. In other words, it's using this simulation as a laboratory to find the building blocks of a new physics. This leads to a really profound shift in perspective, and it's captured perfectly in this quote. The idea is that the fabric isn't just calculating physics, it's behaving like a physical system. It's almost as if each tiny little piece of the grid is its own mini analog computer, all working together inside the main digital computer that's just keeping track of where they are. And that leaves us with a fascinating final thought. If an AI, using these incredibly simple rules, can generate behaviors that look just like fundamental particles and physical laws, what does that imply? Are we just building a clever computer model? Or could we be accidentally discovering the source code of our own universe? It's a question that really blurs the line between simulation and reality. Thanks for joining us.